Yes, please continue.
Okay. So very good morning to all of you once again. Uh, I've already taken one session. That was very nice for me also. I hope you also felt it is useful. So I welcome all of you once again, all the participants. Today, I hope I'm audible and my PPT is visible.
Yes, yes, carry
Okay,
on.
thank you. Okay, so today's agenda is about the hyperspectral image analysis. This is a very uh, uh, emerging topic, I can say, though it is very old, but now also there is a lot of scope. Even you can think to opt it as a PhD topic for your PhD scholar, or if you are research scholar for your own PhD. Okay, so it is a very there are a lot of scopes are there, so we are going to discuss this. Lot of things have been already done, so but it is still not saturated. Today we'll discuss the basics of it. Will not It is not possible to go into deep on this topic. There are a lot of things to be discussed. Okay, so I'll try my best. So let's start. So as usual, I'll just um, switch off my disable my video, and then I'll put it into tab mode. It will be easy for me to explain. Okay. So let us relate with this what we know about the image that is most commonly used image, RGB image. So as all of us know, a standard RGB image has three bands: red, green, and blue. Okay. So how a hyperspectral image is different from the RGB image? So hyperspectral image generally consists of more than 100 bands. Okay, I hope it is very clear in a very simple language. RGB image has three bands: red, green, and blue, whereas there are two other types of images. There is a multispectral images and hyperspectral images. In general, multispectral images have the bands from ranging from 10 to 20. Okay, but today we will talk about the hyperspectral image, which has a band more than mostly more than 100 bands. Even the today the data set what we are going to discuss and basic implementation, that is having a band of around 200. Okay, so you can see the basic difference. So this type of images has been captured by an instrument called imaging spectrometer. Okay, so let us analyze with the help of this diagram. So when we say RGB image, so there is a red, green, and blue band. Okay, and when we take the intensity, then it is a very discrete intensity. We have a three intensity, one for red, green, blue. For example, if you take for some particular pixel, suppose this is the pixel we are taking, the intensity may be something like this. It is having the intensity value of 200. It is having an intensity value of suppose 150, and then it is 170, something like this. Okay, and combination of this will get one color pixel. Okay, in contrast to this, the hyperspectral image may have multiple bands. Okay, may have multiple bands. You can see here there are multiple bands are possible, and then we get the continuous intensity instead of discrete. We get the continuous intensity value. Okay, now how with respect to a little bit about physics, how this hyperspectral image is formed and how it is different from the RGB image. So this is the scenario. So many of these extra bands in HSI, hyperspectral image, now from now we call hyperspectral image as HSI image. Okay, this is the standard. You can see in publication also they write HSI, that means hyperspectral image. so are in the range of ultraviolet to infrared ranges outside the visible spectrum. Our RGB image is inside this small range which is visible spectrum. Okay, but if you see the range of hyperspectral images in terms of wavelength, then it is covering from ultraviolet to near earth infrared range. Okay, so that's why we are capturing one pixel value with several wavelength. Okay, so that's why we are having several bands. So we'll not go into details of it. Maybe some physics faculty will be there, they can understand it more clear way, but for us being a machine learning or this image processing researcher, I think this much information is sufficient. So for us, being a machine learning or image processing researcher, what we need to know, if we know this much, this slide is very important. If we know this much, I think we can proceed with the machine learning implementation with this hyperspectral images. So let us understand this. This is very important slide. A HSI hyperspectral image contains both. There are two terms, spectral and spatial information. Okay, about the objects. So when we capture one object, then we will get two things in HSI image. One is spectral information, another one is spatial information, and combinedly it can be represented as a data cube. Okay, so finally what we'll get? We'll get this data cube. Okay, so a pixel of HSI can be represented with wide range of values collected from different spectral bands and also characterized by several neighboring pixels considered from spatial dimension of the spectral bands. So let us understand this. So when we capture any image, we get one pixel value, and for that single pixel value, we get multiple values. Okay, based on different bands. Okay, it is mentioned represented here. So this dimension is known as spectral dimension. Okay. So if you correlate with this RGB image, so here we have only three bands, R, G and B. So for if you see for only one pixel, so we are having three values. Instead of this, we are having here several values depending on which uh, spectrometer has been considered. Okay, it depends on number of bands, depends on the spectrometer. Okay, so in the spectrometer it has the some limitation or range for the wavelength. Depending on that, we get this number of bands. Okay, so this is about the spectral dimension. Okay, now what about spatial dimension? So suppose let us consider this pixel, then all neighboring pixel if we considered. Okay, this may have same property. Okay, so this is called some spatial, this is called spatial dimension. Okay, so when we work on this type of features, then we call it this as a spatial dimension, and this is its spectral dimension. So I hope it is clear. This is very important slide. If we know this much, it is we can go for its implementation, I think. Okay, so there are two things take away from this slide. HSI contains two things, spectral information and spatial information. Combinedly, it is called as a data cube. Okay, so this pixel width is all bands. So this is one band, second band, third band. Okay, so this is having spectral dimension, and then if you consider this only this, then this is the its spatial dimension. So with this, let us move ahead. So what are the applications of HSI? So these hyperspectral images with this rich information of spectral and spatial, HSI have wide range of applications. Remote sensing, when we access the image from remotely we access like satellite image. Okay, so all satellite images are hyperspectral image. Not all. I just heard a news that recently one satellite has been launched, I think from ISRO, that has the first hyperspectral camera, I think. Okay. So remote sensing images, then environment monitoring, agriculture, biotechnology, medical diagnosis, forensic science, thin films, oil and gas, food sector, defense, security implication, and this is not limited. There are other applications are also there. Here I have just named a few. I have worked on the remote sensing images till now. Okay. So recently I have started working on HSI images. I have worked on only this application, remote sensing application, but you can explore all other applications also. So what is the objective in this all this application? Suppose we captured the image HSI. What is our objective being a machine learning researcher? So objective is the applications of hyperspectral images often require identification of class labels of every pixel in the image. Okay. Identification of class label of every pixel in the image. Okay. So for example, suppose this image is hyperspectral image. Here I have shown only 2D image. It is having actually it is having a several bands, and it is very famous data set. You can find it in many publication of HSI, Indian Pines data set. Okay. I'll also share the link where from where you can download this data set. So in this image, so there are different areas. Okay, so we need to classify each pixel that which area it belongs to, or in technical terms if I say each pixel class label in which class it belongs to. So in all of these applications, one of the objectives, one this is one of the objectives, there may be other objectives also there. So where I worked is only image classification. Okay, so here the one of the objective is in HSI identification of class label. We need to find out the class label for every pixel in the image. So what happened? Manual labeling. People generally do manual labeling. Okay, this area belongs to water. This area belongs to agriculture land. This area belongs to one building. Something like that. Okay. So manual labeling of pixels is time consuming and expensive. So therefore, what we need a classification model. We need a classification model for automatic labeling of the pixels. So we will be provided with some training samples. When I say training samples means some pixels are correctly classified. Based on that, can we label other pixels? Those are our test samples. So that is the idea. So this is one data set, and this is the ground truth of that. Okay, and this is the classification map generated based on some model. Okay, based on some model. So you can see here it is more or less correctly classified. Okay, so this is already given, that's why I'm calling it is ground truth, and this is generated from one classification model. Automatic labeling has been done here. Okay, and you can see here most of the area are correctly classified. Okay, but then what is the issue? You can see there are minor issues like this. See here in this area, you see there is some misclassification. In this area there is some misclassification. Okay, here you can see there is some misclassification. So here our role is how can we improve this classification so that we get very high accuracy. So this is the objective. Okay, I hope it is clear. Now data set. So this data set I have talked about. Okay, this is Indian Pine data set. Now what is the size of this image? This size of the image is 140 cross 145. And what is the meaning of this 200? This data set is having 200 bands. 200 bands. Okay, and these are the class labels. So there are, I think, 16 class labels are there, 16 classes are there, 16 classes. Similarly, there are other data sets are also available, like University of Pavia data set, which is having 103 bands. Okay, and then there are Kennedy Space Center dataset, which is having 176 bands, Serena's dataset, which is having 204 bands. All this dataset, what I have shown, I have provided a link below. Uh, from there, you can download this dataset. So I want to show you this. So just give me 1 minute. you can see this side here. All the there are many hyperspectral remote sensing images have been given with their details. So you can see this is about the Indian Pines data set. Okay, so this is the sensor AVIRIS sensor from which this image has been captured, and all the information, what is its size, what is its uh, number of classes, number of bands. You can see there are 200 bands, and how many classes are there, what are the names of all classes. Okay, all have been given here. Okay, similarly there are Selena's data set, and this is the from where you can download. So this is the link where you can download the data set. So this is your data set corrected Indian Pines, and this is its ground truth, Indian Pines ground truth. Okay, so this is how you can download. So there are Selena's data sets, there are Pavia Center University, Kennedy Space Center, Botswana. There is another data set, Botswana. Okay, so all these data sets are available in this site. I have provided the link here, and it is not that these are the only data set. There are other hyperspectral image data sets also there where you can work on. So our objective in all these data set is to classify each pixel of the image. What is how it is different from the image classification what we have discussed in the last session, which I have taken, how it is different. So there is a lot of difference. Let me little bit explain it. So in the last session we have discussed a problem statement which is image classification. There what was our objective? We had their number of images. Okay, like if we talk about MNIST dataset. So if you remember, there are 60,000 training dataset, right? Okay, and 10,000 test dataset, and correspondingly we have their labels also. So here we have multiple images are there. Okay, 60,000 images, and corresponding to each image we have one class label. Belongs to 7, something like that, and we have 60,000 such images. Okay, and for corresponding to each complete image we have one class label. So this is one type of image classification. Here what we are discussing about the HSI classification. Here overall we have one image, only one image. Here our aim is to classify each pixel. So basically, if you say in a broader sense, it is not a classification, it is a segmentation. We are segmenting the image. Okay, so there is a difference between classification and segmentation. But in standard, if you see, this is called image classification only because we have a label for each pixel. So when we have a label, we are classifying each pixel. You can say, finally, what you can say, it is a pixel wise classification. Okay, pixel wise classification. Whereas this MNST problem, what we have solved, this is image wise classification. I hope it makes sense. Okay, here we are classifying each pixel. So what will be our training data set? Some set of pixels from that image. Suppose Indian Pines data set. So set of pixels will be our training data set from Indian Pines data set. What will be our test data set? So from the same Indian Pines data set, there will be some pixels which will be our test data set. So this is the how it is different from previous model what we have discussed in the last session. Okay, so this was the image wise classification where we have class label corresponding to each image. Here we have class label corresponding to each pixel. Total we have one image. Okay, so this is called pixel wise classification. Okay. So, but there are some challenges in the classification. There are multiple challenges, but these two are the two main challenges in HSI classification. Very first challenge is curse of dimensionality. When we train our model, the dimensionality, if you see in this data set, okay, what is the dimension here? 145 cross 145 cross 200 bands are there. Okay, so if we take each pixel with each band, so there are how many pixels? Lot of pixels will be there, and you train for each pixels. so your model computational complexity will be too high. Okay. So one problem here is how to process this 200 bands. So this is called very high dimensionality problem. So we need to solve this problem. So one solution is PCA. I hope you have most of you have heard about this. This is very old technique and very popular technique still. Principal component analysis. So what we do with the help of this PCA, principal component analysis, we reduce the dimension. Okay, we'll discuss about this later. Then there is a very important problem here that we need to solve: limited number of labeled training samples. If you see the MNIST data set, we had there 60,000 training images. A lot of training images are there to effectively train our model. But if you see here, our objective is to train our model with as less training samples as possible. Okay, so that what will happen when the image will be captured, HSI image from the satellite or from any other source, very less samples we need to label manually, and after that all the remaining samples will be labeled by our classification model. That is our objective. So limited number of labeled training samples, that means what, our training data set should be, training set is very small. With the help of with this very small training set, we have to build a model which can correctly classify other test set. So these are the two main challenges in HSI classification: curse of dimensionality and limited number of training samples. Now, here just I have shown how the HSI classification has been evolved from the literature. Okay, literature, you can say it is a literature review kind of thing. Okay, so initial times, okay, during the early stage of HSI classification, only spectral information were considered. Okay, there is no technique to consider the spatial information. So they have considered only spectral information for identifying the objects through classification methods. Okay, for example, k nearest neighbor, support vector machine, logistic regression, these are the given than other methods. However, the spectral information alone was not able to distinguish different objects, since spectral information exhibit high variance for intra-class and the likeliness between inter-class. What happens? Suppose there are two classes in this image. One image, there is, suppose there is a roof and there is a road with shadow. So maybe both will be classified with the same labeling. Okay, so high variance for intra-class and likeliness between inter-class. Okay, so these are the problem with the when we consider only spectral based HSI classification methods. Therefore, the researchers have, what they have done, they have started using spatial information with the help of gray level co-occurrence matrix, wavelet transform, and other morphological operations. Okay, but then it has been observed that considering only spatial information also makes it difficult for describing all types of objects. We need to consider the spectral information also. Okay, so then the idea came, why not to use both the information simultaneously, spectral and spatial both. And then the deep learning came into picture and people have started working on CNN. So CNN, what CNN can do, CNN can work on like 1D CNN. If you talk about 1D CNN, it can work on the spectral information, and then 3D CNN, it can work on the spatial information. Or we can consider 2D CNN also, we can work on the spatial, which can work on the spatial information. So simultaneously we can work on the spectral and spatial information. Okay, but there are also some issue, or further we can improve this model by using the latest, what is going on in HSI classification model is fusion based HSI classification method. So if anyone is very interested to work on HSI classification, I suggest focus on this method, fusion based HSI classification methods. What is fusion based? What people have done, people have come up with different ideas. For example, why not to extract spectral information separately and spectral features separately using CNN or any other method, and spatial information separately using CNN or any other method, and at the end we can join them all the features, spectral features and spatial features, and classify it. So this is one kind of fusion, and there are a lot of other fusion methods have been there in literature. Okay, so this is one paper I have cited here, very nicely written this paper. And if you go through this paper, you will get most of the idea of latest work on the hyperspectral image classification using CNN. Here he has described the chain author. He has described how 1D CNN can work in HSI, 2D CNN, 3D CNN, and fusion model. Okay, so this is published in IEEE Transactions. Very important paper. If anyone is interested, go through it. Okay, so this is all about the basics or the brief introduction about the HSI and HSI classification. So what we are going to discuss today is we try to implement the HSI classification using support vector machine. Okay, so I have just given here one picture because what I assume is all of you know about concept of SVM. Okay, so how SVM works, what input we have to give. The input will be something like this format, I hope. So there will be some number of samples, 1 2 3. Suppose we have here 1,000 samples, something like that. Okay, belongs to different classes. And then what we do, there will be some features. Okay, suppose you have feature n number of features will be there. Okay, and there will be some values for each feature. Okay, and then finally what we have, class labels. So suppose first pixel will belongs to class 0, second also belongs to class 0, third 1, okay, fourth 2, something like that. Okay, and then 16. Okay, okay, so there are some number of classes are there. These are the class labels. So this is how our input should be. This is the format of input for any SVM model. Okay, so this will be our feature 1. We'll give this to SVM model f2, f3, f4. Okay, so for any image classification also you can do like this, extract some features, make in this format, and then you will provide it to SVM classifier. So with respect to HSI, what we do, we have different bands here. So what I have done here, you need to understand this. It is a little bit complicated, but let me try to explain. So what I have done here, we have 200 bands here. So what we do, we take each pixel value, we take each pixel value and corresponding to that pixel all the band values. That will be my feature 1. Then next pixel value, let me take another color. Next pixel value corresponding to this pixel, all the pixel values of all other bands. This will be my feature 2. Okay, and I'll go on this like this. So how many features will be there? Can anybody tell me? Suppose the size of the this image is m n, and then this is the number of bands b. How many features I will have like this?
M cross N cross B.
M cross n cross b or m cross n? How many features? So this will be my one feature, feature 1, feature 2, feature 3, and then I have number of features here, feature n, and this is my class label. So what I'm doing here, one feature, all the band values, this is all the band values. Okay, so here I am having 200, I have shown only 5. So this will be my one feature. So this is one feature, yes or no? Okay, then next feature. So what will be, how many features I am having? I think I am having m cross n
Yeah,
features.
M cross N.
M cross n features. Okay, so this is how I have converted my hyperspectral image into the input requirement of my SVM. Okay, and this will be my one feature, pixel value, all the band values. Okay, so with this, let us go to the implementation part and try to understand what is hyperspectral. We'll just discuss first the basics of HSI with the help of some implementation. So that will give you more clear picture what is HSI, how it looks. So I'm going to the collab.research.google.com. Okay. So apart from the HSI classification and HSI basics, here I'm sure that some of you who don't know this, Google Colab and all those things, Python, you will learn a lot of many other things. For example, last time we have discussed the MNIST classification, but that MNIST data set is already available in the Keras library. Suppose you have your own data set, how to load into this program or collab. Okay, so there are two ways. One way is you click here in this box what you are seeing, and then it will take some time. The one symbol will come to load the data set. Okay, I hope most of you know this. Yes, this symbol. Okay, so this, when you click here, if you have already have the data set in your folder in your PC, you can select from there and upload here. Okay, so this is one way. Okay, so but what happens, the problem with this is, whenever you close this window, your data will be lost, and once again you have to upload it. So another way is you upload your data into Google Drive. Okay, you upload into data into Google Drive. For example, I'll show you my Google Drive and how I have uploaded the data. So here inside the FDP HSI data, I am already having the data set. These are my two data set, Indian Pines corrected and Indian Pines GT. This is the data set and this is its ground truth. So you can upload any kind of images or any kind of other data set and then directly load it from here. How? Let us discuss. So this is the code which will be common for any kind of data. So here what we are doing, we are mounting Google Drive. Okay, our Google Drive. So this is the code. Just let me run, then it will be more clear. So it will give you one link. You have to click on that link and you go to your Gmail account. That means we are giving permission that you can access my Google Drive. So this is just a authentication, like something like that, permission. So here this is one code that you need to copy. So you just click it here and paste it the box what it is showing. I have put it and then enter. So you can see here my drive is mounted. Okay, content and then drive. So then I have to locate the data what I want to load, the directory for that. So my data is inside the drive, then my drive FDP HSI data. Okay, so let me give that. So CD content drive, my drive FDP HSI data. So I have given the path for my data set. Okay, so it is okay. Now I have to load my HSI data. So this is one way. Any data set you can load it like this, which you already have in your folder or you have in Google Drive. Okay, if you already have in your PC, click here and then you can upload it from here. That is also possible. Okay, now the thing is, when you download the HSI data, what I have downloaded, the site what I have shown, all the data set are in the .mat format. Okay, I hope all of you know, because most of us have previously worked on the MATLAB. So it is a MATLAB file actually. Okay, so you can work on MATLAB also, there is no issue. So how to load the .mat file into Python? So there is a library scipy.io. Okay, and there is a function loadmat. Okay, so I'm importing this library, and then what I'm doing, I'm using loadmat and then file name. Okay, Indian Pines corrected.mat. This is my data, and Indian Pines GT. This is the ground truth. Okay, so this is the data has been loaded. Okay, now there is one issue, since it is a mat file or the format of this file is a dictionary type. So let me show you that. Dictionary type, what is dictionary? Dictionary means there will be some keywords corresponding to that, there will be some values. For example, there will be let me show you that also. What are the keys? So I have written here print dataset dot keys and ground truth dot keys. So you see here there are some headers, versions, globals, all these things we don't need this, all these things for our classification model. What we need only this, Indian Pines corrected and Indian Pines GT. Okay, so we need to remove all these things. So what I'm doing here, I have taken another variable IP underscore data. You can choose any other variable what you want. Then the variable name data set. This is my variable name data set, and there are number of keys are there. What I want here only Indian pines corrected. Okay, so this Indian pines corrected I have just copied here. Okay, similarly for ground truth, what I want Indian pines GT. Okay, so now I have taken into another variable IP data and IPGT. Now if you see the type, that is in our favorable format numpy array. Okay, n dimensional array are there, and this is in numpy format, which is easy to process. Now let us see the dimension. Okay, so print data set shape IP data dot shape IPGT dot shape. You can see here the size of the data set is 145 cross 145, and there are 200 bands. What is the size of ground truth? Ground truth is only 145 by 145. Why it is not there 145 by 200?
Class features.
Class label. Anyone can explain little bit more why the 200 is not there in ground truth? Ground truth we have only 145 145.
Corresponding to every special location of the pixel, we want it to classified as
Yes.
a features.
So, okay, thank you, ma'am, for your answer. Let me explain a little bit more. So, it is something like this. So, this is number of bands 200, and this is 145, 145. So, this is my input image, but the ground truth is something like this only 145, 145. So, what happens here? If you see the class label will be same for all these pixels, yes or no? This is just a same pixel captured in a different wavelength. That's why different bands. Okay, for better understanding, something like RGB, but the class label for that one pixel will be same. It belongs to water or land or some any other object. Okay, so only one. Suppose this all these pixels belongs to class label 1. So one class label. Okay, suppose one more pixel something here. So all the pixels belongs to this, all the bands belong to one class label. Suppose 15, which is some uh, building or roof or agriculture area. Okay, so this is, that's why we don't need, I hope it is clear. Okay, class label for pixels values corresponding to all the bands will be only one value. It is not possible that this pixel belongs to some other class, this pixel belongs to some other class, this pixel belongs to other class. These are the one pixel having different values based on different wavelengths, but class label will be same. It is something like this. One object has been captured, the one pixel of that object has been captured in different wavelength, so class label will be that particular area only. Okay, that's why we don't have number of bands in the ground truth. Now let us visualize it how it looks. So it is not possible for me to explain each and every line, so I'll share this code with all of you. You can go ahead and explore it how I'm doing it. Okay, so let me just run it. What I'm doing here, I'm visualizing how my data looks like. So here, and this is one more thing I want to tell you, how you need to make a function in Python. Okay, so I hope some of you know this. So what you need to do, you need to write define, and then your function name. This is plot band is my function name, and this is the what we call where we pass some values. Okay, data set, and then whatever your function inside the function name. Okay, so when I call this function, whenever you want to call this function, so this is, I'm calling this function plot band, same as this plot band. Okay, and then IP data. That means what I want here, I want to see how my image looks like with respect to any particular band. Okay, so which band I am taking here, you see band number is some random value within the range of dataset dot shape2. What is dataset dot shape2? It will give me 200. Okay, how? If you see here, this is shape 0, this is shape 1, this is shape 2. Out of 200, take any random number, and for that band show me the visualization of my data. So let me see here, this is showing some random band, the band number 3, how band 3 looks like. Okay, and these are the some values. Okay, so suppose you want to see a particular band, what you can do, what I'll do here, I'll just comment it. I don't want random, I want my specific what band I want. So same variable I'm taking. Suppose let us say any random number, some 80. Now it will show only for 80 because I have fixed the band number. Okay, let me run it again. Now I'll call this function. Let me check. See here, it is showing for band number 80. This is the band number 80, how our image looks like. Okay. This is just a visualization of HSI image, because at a time we can see only one band. We cannot see all the bands. So just that's why I have written this function to just visualize how our HSI image looks for any particular band. Now see here, randomly it is given band number 14, how it looks like. And you can also see for different wavelength, different bands, the picture is looking different. That's why we are having here a lot of spectral information, and that will help us to classify any object. Now, so this is about the data set visualization. Let us visualize the ground truth. Okay. So here I have taken the IPGT data set. Okay, and then you see here there are, this is my ground truth looks like. So our objective here is in HSI classification to generate a classification map which is close enough to this ground truth. That is our objective. Okay, if it is exactly same, then we are reaching to the 100% accuracy. That is our objective. Okay. These are some classes. Okay, this area belongs to one class, this area belongs to same class. Okay, this class and this class is same. This is one class, this is another class, yellow, orange, blue. Okay. Now, pixel value extraction along with the class labels. Here what we are doing, the PPT what I have shown you, this. Now we are extracting this type of format. Okay, from the cube, now we have cube. Okay, 155 cross 145 cross 200. That we need to convert into 2D data. Okay, that will be what, 145 cross 145. So that will be how much? Let me calculate. 145 cross 145. So 21,025 cross this, that will be row, and then column will be 200 number of bands, and then for 1 4 we'll discuss that later. Okay. So this is the pixel value extraction. Please go through these codes and explore it. Again, apologize me for not explaining each and every line. It will take a lot of time. Okay, so I have extracted all the pixels. Let us see the shape of my DF, which is data frame. I have converted into data frame. That is one more format. Now you can see here 21025 cross 200. Okay, so I have converted. What I have done here, I have extracted the pixel values from all the bands and put it into DF variable. Okay, now my format is coming into the format what I wanted. Okay, 2D format, 21,025 cross 201. Why it is giving 201? It should give 200 because number of bands. Another one is for anyone. It should give 200. I think this should be number of, this is the number of rows. That means number of pixels in the image, 21,025, and this is the number of bands. That is nothing but my feature. Okay, so 200. But then one more is giving for the class labels. So I have extracted the class label also by using the ground truth. Okay. Now, if you want to see some values, so this is the function df.head, which will give you the first 5 values. Let me check. So here you can see, as I have shown in the PPT. So this is the band 1, all the values, band 2, band 3. Okay, and it will go up to band 200. Band 200, and then there are some classes. So all the first 5 rows belongs to the class number 3. There are 16 classes. We'll see that also. Okay, so this is the function you can use to see the first 5 rows. Suppose you want to see last 5, then there is a function df.tell. You can see here last 5 are there. Okay, 21022, 21024. It is given 21024 because in Python the index always start from 0. And same thing now you can see here the class label are all 0. Now this is all about the data. Now come to the class level. So let us see how many classes are there. So now I'm using unique class labels. I think this I have done in the MNIST classification also. So there are 21,025 pixels belongs to some particular classes, but there may be possibility that many pixels belongs to one class. Okay, so how many unique classes are there? So I have printed that. So there are, you can see there are 16 classes. Okay, 16. So let me uh, count it. So here I have also shown how many pixels are there belongs to each class. So you can see 10,070 776 pixels belong to 0 class, 2000 pixels belongs to 11 class number 11. Okay, there are 20 pixels belongs to 9. That also I have printed here. Okay, if you count, if you sum up this all these pixels, that will come up to the 21,025 pixels. Okay, now this is very important and very good features of Python. Whatever data we have extracted this data set, okay, what is the variable name? Df. This df data set, you can save this as a CSV file. CSV format is nothing but kind of a Excel format. Okay, and you don't need to again run all the codes. Directly you load the Excel file and then start implementing. So here the function is df dot to underscore CSV IP underscore data CSV index false. Why I have written index false? Because I don't want this index. This is the indexing 0 1 2 3 4. I don't want this, so I have written index false here. Okay. So I am storing it IP underscore data dot CSV. Okay, so my this CSV file has been saved into my where Google Drive. Okay, now again I'll go to same path Google Drive and see here. This is the, you can see IP underscore data dot CSV. Now you can download it in your PC and then work it on wherever whenever you want. Okay, so this is all about the basics of HSI. Okay, now let us implement HSI classification using support vector machine. Any doubt or any discussion anyone have, please ask me. Okay, so this is the HSI classification using support vector machine. So same thing, what I'll do, I'll just mount my drive, which is I think I'll already mounted, so it will not, it should not ask. Let us see. No, it is asking. I think I have closed that window, that's why, or open overwrite that window. So let me give it permission to access my drive. Now my drive is mounted. Now I'm giving it to the, directing it to the path from where it can load the data. See here, now I'm not loading the IP corrected data and IP ground truth, because what I have the correct format data in CSV file. Okay, in it is like this. So let me show you. I have already downloaded that file from my Google Drive. I think I have somewhere. Let me check. Yes, it is there. ipdata.csv. I have downloaded it from the Google Drive. Let me see how it looks. And this is the file where we'll work now. So you can see here, this is same what we have seen in Google Colab. This is the band 1, and then we have band 2, band 3, up to how many bands? Let me check. and then their class level. So there are many pixels belongs to class 3, then class 0, class 15, 11, 3, 15, 11, 0. Okay, so 12. Okay, and what is the, how many rows are there? There should be 21024. You can see here 21026 rows because we started from 1. Okay, 2. That's why 21026. So this is the Excel file which will, so for any image classification also, suppose you are implementing support vector machine or any traditional classifier, then what you can do, you can extract the feature. Suppose you have extracted color feature, then mean, variance, shape. So that should be, the format should be like this. This is the feature 1, all the values for all the images, then feature 2, feature 3, and then add then class label, and then you can feed it to the your model. So let's go back to the code. Here what I'm doing, I'm importing my CSV file. So there is a library, very famous library, pandas. Import pandas as pd, then pd.read csv, and here I have loaded the file. Let us once again check it has loaded the correct file or not. Yes, same data set what we have seen, it is showing us. Okay, so here you can see there are 200 bands and the number of classes. Okay, let us check the shape of it. Then same shape, 21,025 and 201, 200 bands, and last one column is for the number class labels. Now what I'm doing here, since I have to give it to SVM, support vector machine. So in support vector machine, I should have, before giving it, I need to divide into training and test set. Okay, so I need to divide the data set separately. Like all the data will be in one variable, all the class labels will be in one variable. So there is a function iloc, okay, that will extract all the column, all the rows, okay, values. So what I'm doing here, data df.iloc, then this bracket and then values, and then I am loading it here. So everything looks same here, df iloc, here also df iloc, everything same dot values, but then how it is extracting data here, how it is extracting label here, there is one minor difference. So now you see in my data.shape is 21, 25, 200. Now I'm having only features, I don't have here class labels, and the label I'm having 21, 25, that means it is having all class labels. So what is the difference between these two is, what, how I have written here, colon means all rows, but what I'm taking column, all colon, that means all rows except -1. So that means except last column. And here what I have written, I have not written colon here, I have written only -1, that means only last column. So labels will be extracted in, labels are there in only last column, and data will be there from first column to except last column. Okay, so now I got all the data will be in my variable data, and all the labels will be in the labels. Now let us check how many classes are there, how many unique labels are there. You can see here there are 16 class labels are there, and there are, these are the unique class labels. Now I have to divide this into training and test data set. So I hope you know this very famous library for basic machine learning or traditional machine learning as Scalar. This is very good library to work on the traditional machine learning like SVM, decision tree, random forest, KNN, or any other classification thing. Okay. From scalar, what I'm exporting, train test split. Okay, train test split. So this will divide my data set into training and testing. So I have storing my output variable into xtrain, xtest. This will be my data. Then ytrain, ytest corresponding labels, and then I'm also storing some indices. That means what are the indices, that means pixel index of belonging to training, pixel index belonging to test. We'll discuss the importance of these two later. Okay. So now I'm using train test split function. I'm giving here data and label, and then what I'm doing, test size equal to 0.2. What is the meaning of it? Test size equal to 0.2. The meaning is that 20% of total pixels, that means 21,025, I'm keeping it as a test data, and remaining 80% as a training data. And then random state, any value, any value, you can just discuss in brief what is the importance of data mixed state also later. Now let us check xtrain and xtest. Okay, it is giving it. Okay, I have not run that actually. Just explain it. Let me run it. Okay. Yeah. Okay. Fine. Let us run the train and test set. Okay. So it is. So let us check. Suppose if you want to check it from the 21,025, what I have done, I have taken 20%. That means 0.2. So here you see 4,205 is my test data and remaining 16,820 is my training data. Okay. Similarly, you can get the class label also. Here you can see 4205 corresponding class labels are there as a test data and remaining as a training data. Now we have to apply it into support vector machine classifier. Okay, so this is the again sklearn we can use sklearn.svm import svc.
Excuse
svc,
me.
yes, yes, ma'am.
Here actually we are supposed to classify each pixel belong to which label.
Correct, correct, ma'am.
Actually, if you look at the data, what we find that in class in label 0, we have a very huge number of pixels. In label 2 or 1, there are very less number of
Correct,
pixels.
correct.
Won't it create any problem? Maybe data imbalancing, something
Yes,
kind of
yes,
thing.
yes, it is. Yes, it is there, ma'am, and it is. We need to
And you
develop a
done
model.
something to handle that
No,
imbalancing in data.
I have not worked specifically on that, but there are techniques to handle the class imbalance issue. Like there is a technique upsampling and downsampling. You can go through it, but I have not done that. So
Without
even
that, does it provide good result?
yes,
Means
yes, yes, yes,
performance?
yes, 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 ma'am. Yes, but it
Okay,
still,
okay.
if you include that technique with
That
the
will be
model,
better.
that may improve further
Okay.
performance. Okay.
Okay, sir. Thank you.
Thank you, ma'am. So let us apply support vector machine to this data set. From sklearn.svm, I'm importing SVC. SVC is support vector classifier. There is also SPR. If you are working with regression problem, then you can import support vector regression. Okay, I hope you know the difference between classification and regression. So here I'm using support vector classifier with RBF kernel function. So you can use different kernel function. There are linear kernel function, polynomial kernel function with different orders, RBF, which is nothing but radial basis function, or Gaussian kernel, and there are multiple kernels. Even you can develop your own kernel. That will be one novelty. Okay. And then I have used one variable here. Any variable you can use as a classifier. And now I am training my model using xtrain and ytrain dataset. Okay, so classifier.fit. What is my classifier? It is nothing but the support vector machine. So it will take some time to train my model because it is having a huge training dataset, which is 80%, 16,000 datasets are there. Let us discuss further so that we can save our time. Then what I have done after training, I have just predicted the my test data set. So here you can see classifier.predict, and I am not giving the ground truth for the test data set. What I'm doing, I'm just giving my testing data set. The objective here, my model should predict the class labels. Okay, so that I'm storing into the y predict label. Okay, so here my model has been trained now. So I have given only one parameter, which is kernel function. You can see here kernel RBF. So there are many parameters in SVM. You can play with that and experiment which is better suited for your data set. Okay, so there are like C value, gamma value, degree, and there are so many things. But I have made it very simple. Just given the RBF, and all other things are by default values it has taken. Now let us test my data set. So it will should not take time because there are only 4,000 pixels that it will classify. based on my trained model. So it has been classified. If you want to see the values, that also you can see. Okay, so just you need to write y predict. You see here, it is the there's like first pixel, it has been classified to class number 11, second pixel 8, and so on. Like this, there are 4205 test labels. Okay, now I have to check the accuracy. Very simple. We need to import the accuracy score. Where is the library? Let me check whether I have imported it. No, I have not imported it. I need to import it. Let me. Accuracy score. So what I'm giving here, accuracy score, I'm importing a library which is under the sklearn.matrix accuracy score, and now I'm giving here the true class labels which is stored in the y test and the predicted by the model, the class label predicted by my SVM model y predicted, and it will compare these two and give me the accuracy. So here you can see it is giving very low accuracy of 61.54%. Okay, so why it is giving very low accuracy? There are maybe multiple reasons. One reason is we are considering only spectral information. We are not considering any spatial information. Okay, and there are other reasons also there. Like SVM is maybe not able to classify. We need to go for the better model, or like ma'am said, we need to solve the class imbalance issue. So you can work on it. Okay, so this is the accuracy we are getting. Now in the last session, what I have taken, many participants have asked me about the other classification property. Now I have come up with that also. So you can apply this classification other parameter in MNIST dataset also. You don't need to change anything. Just you just copy paste and you will get the all the results. So what you have to do, sklearn.matrix says import classification report. If you just import this and implement this with the same variable y test and y predict, you will get so many other parameters. Like you can see here, what is the precision value for each class, recall value for each class. There is F1 score support. You can go through this, what is the meaning of it. Precision and recall, very famous parameters for classification. Other parameters are less used, and you can see here it will directly give you the accuracy also. See here, this is the accuracy, 62% accuracy for the 4205 test dataset. And there are other kind of accuracies are also there, macro average and weighted average, that also you can go through it. Okay, so either you can calculate the accuracy using this, it is also giving 61.54, or simply classification report. Matrix also very famous parameter for classification model. So here how I have plotted the confusion matrix here, very important thing to be noted down. uh, all the libraries, most of the important libraries are installed in the Google Colab. That means the server of their Google Colab. But if some function you want to implement and it is showing, suppose I'll just comment it and then I'll try to run it. Let me check whether, see here it is giving the error, no module name scikit plot is available. So if you are getting this type of problem, that means this library is not installed in Google Colab. Then you need to install it. How you need to install it? So easily you can get in the net what is the function. So this is the function pip install q scikit plot. So like suppose you are working in Python in your PC, not in Google Colab. So how you install the libraries in PC, same way you need to install in Google Colab server. Okay, so now this is the way I am installing it, because it is not available in the Google Colab. And then I'm importing this sk plot matrix, plot confusion matrix. What I need to give, y test and y predict, and then the figure size. Okay, so let me check. Yes, now we got the confusion matrix. So you see here, these are my two labels and these are my predicted labels. So you see here, the zero class is mostly correctly classified, more than 1000, no, not correctly, there are 10,000 pixels, but only 1991 are correctly classified. I hope you know this. All the diagonal elements of any confusion matrix will show you the correctly classified values. Okay, all the diagonal elements of any confusion matrix will show you the correctly classified pixels. Other than diagonal elements also show you the misclassified pixels, and also misclassified to which class. For example, suppose I'll tell you one thing. This 94 is belongs to the class label 2, and it is correctly classified as class label 2. Okay, but this 63 is actually belongs to class label 2, but it has been classified as class label 0 by our model. I hope you are getting the meaning of confusion matrix. Okay, suppose this 32, correct class label for 32 is 0, but it is misclassified as class label 2. Okay, this is how you can interpret the confusion matrix, and you can calculate the accuracy from confusion matrix also. How you can calculate the accuracy? Sum all the diagonal elements divided by sum all the elements of the confusion matrix. That will give you the accuracy. Okay, so this is how you can calculate other parameters for any classification model, not only this HSI. You can implement all these programs into your MNIST classification or any classification model. So this is all about the parameter. Now we need to check the classification map, how it is looking. So you can clearly see the difference here. This is the ground truth classification map, okay, which I have already shown. Now here I have what I have done. I have extracted the labels of the pixels of my classification map. Okay, so since we have, our model has predicted only classified label for class labels for only 4200 pixels. What about 16,000 pixels class label? So for those 16,000 pixels we will take the true class labels, because those are the training. So here I have written a program for those 16,000 pixels, take the true class labels, and remaining 4,000 pixels take the predicted class label by the model. Here comes the those two parameters what I have told you, indices of training and indices of training. Let me go back and remind you that while training testing I have saved two parameters, indices train and indices test. These are the indexes of the pixels which are belongs to train data set and which are belong to test set. Okay, now same indexes or indices I am using here. Okay, this is the indices train, because how I will know? Because when you divide training and testing, it will be divided randomly. So how will I know which pixels belongs to training set and which pixel belongs to test set? So the indices train take the true labels, and for the all test indices take the correct labels. Sorry, take the predicted label by the SVM model. This is where it is giving. I think. Map, the pixels are classified by our model for only for test data set. Okay, so you can clearly see the difference here, because accuracy is very low. So this is my actual ground truth, this was my objective, but now what I'm getting is like this. Okay, can you see the difference? There are many pixels which are incorrectly classified, that's why we are getting this type of images. There are many places which are not correctly classified. This is all about how you can go for the HSI classification using SPM. And similarly, you can just change this part. Yes, you need to change this part. Yes, here. Just to change this part to KNN. Your model, you will get the accuracy for KNN, the decision tree, random forest, and then all the parameters you can calculate using the same program. Just change this part, and then you can present one comparative study, because when nowadays CNN are mostly used. Okay, so what you can do, you can develop a CNN model, and then you have to compare with other models. So you can compare with SVM, decision tree, random. So this is the program from where you can generate your benchmarking table. Okay, now there is one more thing. Since we have taken here training testing 80% as training data set and 20% as test data set, but actually what should happen here, as I mentioned in my PPT, our test data set should be our training set should be as less as possible. Okay, I hope you are getting. For HSI classification, we should have only like something like this. Our training data set should be 20% and test data set should be 80%. That means my model should be efficient enough to classify, to generate a model using very less training samples. So now let us test with this quickly. I'll calculate the accuracy only. All other parameters you can calculate. So I have again divided my data set into 80% as test data, 20% as training data. Okay. So now if I run this model, okay, the model is trained. It has not taken much time this time. Why? Because there are very less training data. 4,000 training data are there. 60,000, 16,000 are test data. Now it will take some time because there are many pixels are there. So when you go for the HSI classification, try to follow this. Take very less training data, and that is also one of the objective of HSI classification. Can you get high classification accuracy with as less training samples as possible? Okay, now you see the accuracy is further decreased. Why? Because my training data has become very less. Okay, 58%. So this is one thing. And the last thing about the implementation part is you can work on the PCA. There are 200 bands. What happens when we have a lot of bands, 200 bands? There may be some of the bands which are um, not very useful for us. There may be noisy bands, so you can reduce the band, but it's not that randomly you reduce the bands. So there PCA comes into the picture, and you can utilize the PC. What PCA does? It will select some important bands. Now I have reduced to here. I have taken 100 components. Now my bands have been reduced to 100. Now how many features I am having? Only 100 features. Previously I had 200 features. Now this PCA, what it will do? It will select the band. It will arrange the order, arrange the bands in a decreasing order, being the first band having the highest variance. Second band is the less variance than the first band, like this, because the band which is having more variance, which is useful for us for any classification model. Okay, I hope it makes sense. Our feature should have more variance, then only we can classify better. Okay, now I'll take the same test set radio test ratio. So this is 0.8 I'm taking. Let me quickly calculate the same problem. So I have divided the data into training and test set. Now let me run the model. So you can see with the help 64, the accuracy has been a little bit
Hello. Is it audible or
No,
low?
ma'am, not audible. Not
No, ma'am.
audible.
No, ma'am,
Oh,
not
wait,
audible.
wait, wait. Let me. Just give a minute. He's again reconnecting.
Okay, sorry about that. Somehow it got disconnected.
Okay, you're
So
back.
let
Okay, carry on.
me again say, yeah. Okay, so I hope my screen is visible. Okay,
No, it is.
so see here
Are you
with
getting the
the
screen?
help
Yeah,
of
it's
PCA, we can.
wait, wait, wait. Let the screen get visible. It is. Yeah, now, yeah, continue. Carry on.
Oh, okay, okay, ma'am. So this is all about the implementation part, and same way you can calculate the pixels and matrices and all other pixels and map and all those things. So if you have any questions, please ask me. Otherwise, I'll just move forward to few slides where I'll show you just brief about the how you can apply CNN in HSI classification. Any questions regarding implementation part? Okay, so I think there is no question. So let me share my slide once again. Yes, please.
No, you go to the
So
slides too.
here we have
Yeah.
seen the SPM. Okay. Okay. So here we have seen the SPM where we have used only spectral information. So these are the spectral information band. Now suppose you want to work on the spatial information, you can work on the CNN, HSX, and this is the recent trend. Everyone nowadays is using CNN for HSI classification also. Okay. So here, and it is very, it is not an easy to show you the implementation of it. It is a long procedure you need to apply. So since this is the how hyperspectral image looks, what we are doing, we cannot work on all the bands. So we are applying the PCA and only selecting the first band, only selecting the first band. This is one idea. This is not that the fixed procedure you need to follow. You can have 3 bands also, 5 bands also. It depends on you. This is one idea what we have done and published one paper on this. That what I'm showing. So this is kind of our work. Okay. So we have selected first band which is having the highest variance. Okay, and then we have extracted some patches from that because you know that how CNN works. CNN works in some kind of
Sir is not audible. I think again he has some network issue. Bimal, I can't hear you.
hello ma'am, is it audible now?
Yes, audible.
No, Bimal. Again, you have to check your audio jack. Hello.
Ma'am, is it audible now?
Now it is audible, but again and again you are getting disconnected. Check your audio jack.
uh, Ma'am, actually some internet issues there. Is it okay now?
No, your
I just take 10
slides we could
10
see,
20
but
minutes
the
please.
voice was not coming. Yeah, it's okay. Carry on.
Okay, so I hope I'm audible clearly now. So
Yes.
what we are doing here, we are extracting some patches here. Okay, so what we'll do, we'll extract some patches and then, so suppose I have extracted some one patch from this side, and then suppose there is a, we have taken 27 by 27 patch. Okay, and the center pixels, the class level for this complete image, the class level of the center pixels we have assumed as a class level for this complete image. Suppose the class level is 0, then for this complete patch we have assumed the class level is 0, then we have moved it to slide 1, then this next patch we have taken and center pixel class level we have assumed it to class level of the complete image. So this is how we have form our image suitable to the CNN model, and this is the method several paper has applied. Okay, you can see that, and then we have applied the deep CNN model to it, and this is the features of our deep scene and model. We have convolutional layer with 32 filters or kernels stride of 1 4x4, and then max pooling 2x2, then again convolutional layer, pooling layer, convolutional layer repeated, and at last soft layer. So this is the model what we have developed. We have worked on the several hyperspectral images, and then our objective here is of course to get the high classification accuracy, but other than that there one more objective we had here. What we have done, we have compared different pooling strategies. Now what in general we know there are two pooling strategies, max pooling and average pooling, but apart from that there are other pooling strategies have also been proposed in the literature. So it is not it will take time to explain you other pooling strategy. I'll just give you the name, you can explore it from my paper or from any other literature. So our objective is, if we change the pooling strategy and then apply this HSI data set, how the classification accuracy affects. Okay, so this is the first work what we have done, analysis on effect of various pooling strategy. So there are broadly two types of pooling strategies. One is value based and other one is rank based. So this is nothing but the value based. Max pooling is based on the value, maximum value you are taking, average based on. There is another category is stochastic pooling strategy. You can go through it. And then there is a rank based average pooling and rank based weighted pooling. So we have compared these 5 pooling strategies and got this result on different HSI classification data set. Like there is a Indiana points, what we have discussed. There is a Kennedy Space Center, University of Pavia, and SA. And this is the classification accuracy we have got for different pooling strategy with the same model. Model we have kept same filter size, same convolutional layer, same number of patches, everything same. Only we have changed the pooling strategy, and this is the accuracy we have got. So for most of the things, what we have again got the same thing. For max pooling, most of the things, max pooling is giving the best accuracy. Okay, so this is based on this analysis. We have published one paper. Okay, you can go through it. This is the effect of pooling strategy on convolutional neural network for classification of hyperspectral remote sensing images. And this analysis can be done for other data set and result may vary. Okay, and we have published into one SCI Index journal, IIT Image Processing. Similar kind of work we have done where we have fixed the same model what I have shown you, but compared several optimizers. Okay, because what we have found is for HSI data set, different optimizers have not been analyzed. Okay, so we have compared 7 optimizers. So this is the result what we have got. This is the stochastic gradient analysis and optimizer, ADA grade, ADA delta, RMS prop, ADAM, ADAMAX, and NADAM. Okay, these are the 7 optimizers we have worked on HSI classification, keeping the our model fixed, and this is the accuracy we have got. So what we have analyzed is for most of the cases, ADAM is giving the best accuracy, and based on that, we have published another paper in International Journal of Remote Sensing. Okay, this is very standard journal of any remote sensing publication. So this is another work we have done. Okay, now so this is all about the HSI classification. Last 5 minutes I will talk about another totally different scenario of HSI classification, which is called active learning. It is totally based on one sentence that I have mentioned in my PPT, limited number of training samples. And our objective is to classify to the HSI data with high accuracy by using as less number of training samples as possible. So with this concept, one technique has been developed, active learning. What is active learning means? Can we select most informative samples as our training data set? And based on that we train our model and then try to classify other pixels. Okay, once again I'll repeat, this is very important. Can we select most informative pixels? Now what is most informative pixels? What can be most informative pixels? So which is having some uncertainty. Uncertainty means what? Suppose there are a number of pixels, but there are some pixels which are difficult to classify. Okay, which are not clear, which may belongs to, it seems like which may belongs to many classes, 2 different classes, which are uncertain samples, so which are difficult to classify in general language. Okay, those should be my training data set, because if my model is able to classify this data set which are obviously belongs to some class, easily they can be classified. For example, let us just, I'll show you one thing. So suppose this is my data set. Suppose generally whenever we explain the classification, you have seen video also, we explain with the help of binary classification because it is easy to explain. These are the two data set, one is star, one is circle. Okay, now I want to classify it. Okay, so which is most useful sample for my training? Can anybody tell me which will be most useful sample for training? Okay, so these samples which belongs to near to the boundary line, this will be my most useful sample for training, because these samples are obviously easily classified. We can easily classify, any model can classify. If you apply any classification model, KN and decision tree, easily classify. The most difficult to classify is this type of sample which are near to boundary line, so which are uncertain. So this is the technique which have come into HSI classification, and there are a lot of papers you can find on active learning, HSI classification using active learning. So the idea is something like this. This is the model of, we divide our data set into training samples and test samples.
Excuse me.
Yes,
Excuse
please.
me. I want to ask one question over here.
Yes, sir.
The most informative samples that you described now, which are near to the boundary of two classes, right?
Yes,
Uh,
right, correct.
Yeah, isn't that these are the support vectors of the SVM that the SVM learning?
Sir, you are saying very correct, and this support vector, that concept what you are telling, that has also been used as a active learning model. So what they do, they classify the model, and every time support vectors they choose as a most useful samples, most informative samples. I'll come to that also. Just give me 1-2 minutes. I'm coming to
Okay.
that. You are saying correct, support vector, but it's not always support vectors, because when you are using SVM, then only these are called support vectors. When you are not using SVM, then what we call in general most informative samples. Okay.
Okay. Okay.
Okay.
Okay.
So what we do, total data set. Suppose we'll take the example of Indiana Pines. So we have total 21,025 data set. So we'll divide this data set into training and testing. Suppose that my training data set is something training, C train, and then C test. I'll keep my test data set separate. I will use for it for testing. Okay. Now how my active learning training in active learning scenario will happen? I'll further divide this training data set into two parts. One is very small labeled samples or a small set, and another one is big set. For example, I'll take only 5%, only 5% or less than that also you can take 5% data set into initial training data set. It is called initial training data set, and remaining 90% from the training data set I'll keep as a unlabeled sample. I call it as unlabeled, though we are having label also. The reason behind that is, okay, there is unlabeled sample. So what I'll do, I'll first train. Now here I can use any classification model. SVM I can use ELM, extreme learning machine, I can use decision tree, or I can use any classification model here. I'll train this model with the help of very small training data set. Then I'll get the accuracy of this test data set. So what I'll do, this is the iteration 1. Then I'll get some accuracy here with the help of this model on test data set. Then what I'll do, I'll just test on this data set also, unlabeled samples, and try to find out which are having the which is difficult, which pixels are difficult to classify. Those pixels I will take as a next set. So this is called query strategy. So whatever strategy, with the help of any query strategy, you can find out which are the most informative samples. So here is one way where you can focus on the research. How can we choose the most informative samples? So this is one way. What I'll do, I'll take those informative samples and I'll fix at the starting. I will select every time, suppose 5 pixels. Okay. Now those 5 pixels which are most informative samples, I'll assign true class label to it, and I'll add it to my this small label training samples. Again I'll train it, then I'll get the second iteration, some accuracy. So my accuracy will definitely improve. Okay. So in this way, at how many less iteration it will take, and I'll reach to the maximum accuracy 95 or something. This is my strategy. So there are multiple methods have been developed. This is the random sampling based active learning. This is one basic method from where you can compare your model. Okay, this is random sampling means what? Randomly we'll select some uh, most informative samples. Okay, so I'm not going to details of it. This is one strategy, very important strategy, multi-view. So let me just give me 5 minutes. I hope I can take 5-10 minutes if you allow me. Okay. So what has been done here, multi-view. So suppose we have 200 bands, 1 to 200. Based on the analysis, what researchers have found, there is some correlation between the some group of bands. So there is suppose 1 to 11, one group, 12 to something 20, one group. So this is how these are the one correlation is there. So why not to have multi-view? So this will be my model 1. This will be my model 2. This is how you can generate multiple views. So let me explain with the help of this. So what I will do, I will I have different models, model 2, model 3, model 4, model 5. Okay, this model 1 is based on the my first view. Okay, I'm calling it as view 1. Okay, now I'll train my data set, a small level data set, and then I'll find out the maximum disagreement. What is maximum disagreement? From the unlabeled samples, when I test my model, I'll get the class label for each pixel. So I'll choose the pixel which are having something like this. My one model is classifying same pixel as class label 1. Second model is classifying same label as class 2. Third model is classifying same pixel as 4, 5, 3. Now there is another pixel which is having 1, 1, 1, 2, 1. Now can you tell me which one will be useful for me? This pixel will be useful for me, or this pixel will be useful for me? For one pixel, all the 5 models are able to classify approximately same class 111. One model is incorrectly classified, misclassified it, but there is one pixel for that all the models are giving different class label. So this is what my most informative samples, because it is difficult to classify. So this is called maximum disagreement between all the models, and based on that we select the most informative pixels, add it to the this set, again train it. So what happens at the end, what we will get? We'll get something like this. This is my accuracy, and this is my iteration. So iteration by iteration, this is iterative process, I'll get the accuracy. So at the end we'll see, suppose in 100 iteration only we are getting the 95% accuracy, and each iteration suppose we are adding 5 pixels, then around 500 pixels only we are able to get 95% accuracy. This is the active learning. Based on that also we have published some papers. So these are the totally complete scenario active learning, and there are a lot of scope to work on that. So these are some publications based on only HSI classification. So these are the 2 papers which I have already shown: analysis of pooling strategy, analysis of optimizer, and these are the papers where we have worked on the active learning. Okay, so this is also IT image processing published, and then kernel based extreme learning machine we have applied for based on the active learning. Okay, and these are also one conference paper based on active learning, and this is the recent published book chapter. We have published a book chapter on active learning. So I suggest or request you, all of you, that please, if you are anyone is interested on active learning, if you go through this book chapter, it is having all the information about active learning from starting to end in a like a book chapter has, so in a sequence you can get it. Okay, so all the things are there. Okay, and these are the 2 papers I have put it here in the PPT, very useful if you want to work on the HSI classification. So this paper, what I found, is very good for deep learning. If you want to work on deep learning on HSI classification, this is a review paper. Okay, a deep session, and this is one paper based on the active learning. This is a survey paper, very nicely explained about each and every concept of active learning. So please go through these 2 papers if you are very interested in HSI classification. So this is all about HSI image analysis. I hope you have got some idea. I know this is not an easy concept to explain in 1.5 hours. So I tried my best. I hope you got some idea about all these things. So please, if you have any questions, you can ask. I'm happy to answer.
Yeah, any queries?
Is there different optimizers that you have used for the classification?
Yes,
the SGD, ADAGRAD, then ADAMAX, all are available in the scikit package. Like,
it is not in scikit package, but yes, it is available in Keras. But pooling is not available in Keras. Only max and average pooling are there. For other pooling, we need to write programs based on the mathematical equations.
Okay. Thank you.
Any more queries? Okay. I think it is completely in a different domain. Yeah. Pranati.
So, can you
Okay, Lalita.
yes, can you say something about image augmentation, where how it is related to transfer learning or active learning? Do I need image augmentation in all time?
Yes, ma'am. So image augmentation. So there is a one simple
The
method
question is in general, you're asking for image augmentation or image augmentation for hyperspectral images?
Yes, image augmentation for HSI images.
Okay.
Ma'am, I will not be able to answer about HSI, but in general, I'll tell you what happens generally. When we have less number of samples, we need to increase the number of samples for our for improving the classification performance of our model. Okay, so what we do, we apply the image augmentation technique. So there is very basic techniques like transformation. So we rotate the image, we flip the image. Okay, because by rotating also our model should be able to classify it correctly. Okay, so we apply some basic transformation. This is the basic image augmentation techniques. Then nowadays a very new techniques have come, which is GAN, generative adversarial technique, neural network, generative adversarial network. So using GAN also you can generate different images. Okay, and then you can have more data set, more samples, and you can work on it. In general, I can say I have not worked on HSI, so I will not be able to answer that.
Thank you, sir. So one more question. What is the difference between active learning and transfer learning?
Ma'am, there is a totally two different thing. And transfer learning, what we do, we take a pre-trained model, and then we kept the weight of some layers of the weights constant. Constant means fixed. It's not constant, fixed from the pre-trained data set. Okay, and for the only few last layers, we run our model and train it. That is called transfer learning. Whereas active learning is a totally different thing, where what we are doing, iteration wise, we are updating our training data set, and the objective is to have a effective training data set which is having less samples but effective samples. That is the objective.
Okay, sir.
Any more
Thank you,
question?
sir. Thank you.
Any more question from anybody? Yeah, I think that's all. So Dr. Bimal Srivastava, thanks a lot for introducing and talking about a new domain. Many people don't start research in this domain considering the fact that availability of data, availability of ground truth. At least you showed the links from where the data can be taken and further analysis can be done to compare it with the ground truth. So thank you very much.
Thank you so much. Thank you all the participants.
So participants, so that is the end of this second session of the final day. See you all at around 3 p.m. So I'll just briefly discuss about this LSTM model that was not in the original plan. So meanwhile, I received some requests from a few participants. That is why I'll be considering that one. And quickly for 1 hour only, I'll show what are the issues with the LSTM and how those can be handled. And thereafter we'll have the valedictory session where I would like to request all of you to give your feedback not only in a Google form where you will click something and kind of MCQ, but also your verbal feedback, which I would like to record. Okay, that's it from my side. So see you all at around 3 p.m. Any queries from any one of you?